All right, the pigeonhole principle is something that's used for a specific type of counting problem that you might come across. So the fundamental idea of what this is really simple. We can think about where this name comes from. I'm not sure the whole history on it, but the idea is, let's say you've got 3 pigeonholes, and I'm not even sure what a pigeonhole is. So 3 pigeonholes. And the question is, what's the minimum amount of pigeons that are necessary to where at least one pigeonhole has more than 2 pigeons? So there's some amount of pigeons with the requirement that every pigeon is going to go into at least one of the holes. And so what's the minimum number of pigeons, of total pigeons here, that are necessary to where at least one hole is going to have 2 pigeons in it? And so, this is a pretty simple problem here. We know the answer is going to be 4. And so the idea is you could have all 4 go into one pigeonhole. Well, then there you go. At least one pigeonhole has more than has 2 pigeons. Okay, but the worst case scenario would be that the pigeons spread out as evenly as possible. So you get a pigeon here, and a pigeon here. But then now that 4th pigeon is going to have to choose one hole. So one hole is going to have at least 2 pigeons. Okay, and mathematically, the way we look at this problem is, with pigeonhole problems, you're using the ceiling function. So there's the floor function and the ceiling function, and both are really simple. The whole idea is, if you've got you could put any number you want into these functions, decimals, whatever, but if you've got something like 2.73 and you indicate the ceiling function like this, the floor function would be like this. So 5.02. Okay, all you're doing is, with the ceiling function, you're rounding up to the next largest integer. You don't just round. If you have like a 5 here, no matter what it is, this would be equal to 3. If you had 14 point, then this would be equal to 15. Okay, the floor function is just you're rounding down to the next lowest integer. So even if you had 18, right, and you had a floor function here, then this would be equal to 18. So the pigeonhole principle uses the ceiling function, and the whole the idea is, for this problem here, we would have. So the question is, how many pigeons are necessary to go into 3 pigeonholes to where there's at least one hole has 2 pigeons? Then you write it this way. It's the ceiling function. You have the number of pigeons divided by the number of pigeonholes, and that's going to be equal to some number, right? And so the 3 variables here, you could, with any pigeonhole problem, you could be solving for any of these 3 variables. This would be, so we said 2, right? We said to where there's at least one of the pigeonholes has 2. So C would be 2 here. Okay, and then there's 3 pigeonholes. Okay, and so we're solving for n, right? And I'm not going to get into the specifics of solving a ceiling function when you've got a variable inside of the ceiling function. I think you should be able to to critical think and figure that out on your own. That's really simple, right? So what's going to be a whatever n here, n divided by 3 is some number between 1 and 2, including 2 but not including 1, right? N is going to be, it could be equal to 2, but it can't be equal to 1, or else the ceiling function would be equal to 1. Or no, wait, that's not right. No, this is n divided by 3. So I guess I am sort of going into the specifics a little bit, but n divided by 3 can be exactly equal to 2, that's fine, but then, or it can be greater than 1, not equal to 1. So if we multiply this entire 3-part inequality by 3, we've got Okay, but now the question was, we're looking for the minimum amount. So we can't say 3. So what's the next? And we're dealing with pigeons here, so we're thinking about integers. So it's 4, right? The answer is 4. And so with a pigeonhole problem, you could be having to solve for any one of these variables. It's going to be easiest when you're solving for C, right? Because then you just evaluate the ceiling function. So again, let me make sure this is clear. You can have, for a problem, there can be any number of pigeonholes, any number of pigeons, and any number, so like a minimum of, every hole has at least 3 pigeons, or at least 5 pigeons, right? Those are the 3 parameters. A number of pigeonholes, which could be, that's variable, a certain number of pigeons, and then a certain minimum amount, like there's going to be at least one of the pigeonholes has this many pigeons, so whatever C is. Just one of the pigeonholes has this many pigeons. So you could put all the pigeons into one hole, that satisfies the criteria. So it's all about, okay, you spread them out as much as you can possibly spread them out, but no matter what you do, you can't get around one of the pigeonholes having C pigeons. All right. So this is pretty straightforward, the logic behind this. But what can make actual problems a little more complicated is a same confusing factor that can also make general counting problems difficult to solve. And so what can make it difficult is that, so we know from a general counting problem, we can have an event diagram here, which you could also make it like as a Venn diagram with these Venn circles, but here's just a general event diagram, right? Event 1, event 2, event 3, okay? And you determine if these events are connected or not, which means you're going to apply the product or sum rule between them. Maybe these two are connected and E3 is not connected. But then it's like you're going to go to a separate page in your notebook and get a full count for event 1. That's going to be one, that could be its own type of counting problem with permutations, combinations, whatever. And same thing with event 2. Maybe event 2 is going to be a pigeonhole problem. So you'll have that there's a count, M outcomes here, N outcomes here. You do the same thing with event 3. G outcomes here, right? And so when you go to a separate page in your notebook and you're doing a counting problem, a typical way you're going to approach a lot of problems is with these sort of slots here. And you're usually you're applying the product rule between these slots, and if you're going to be doing the sum rule, you'll do the sum rule off to the side with like some separate slots or something, or you could do the sum rule between the slots here, but so we'll call these slots, right? Maybe you're putting letters here, whatever. But sometimes we'll call these bins. Sometimes you'll hear these called slots, bins, and you'll hear that you're pulling objects, and you might call what you're pulling the objects from a bin as well. You're pulling objects from a bin, right? These terms are getting mixed in everywhere, these same terms. And I've mentioned that you're going to have, whenever we start working example problems, you're going to have to learn to be extremely flexible with how you use the term bin, the term object, the term element. Because, for example, the combinations with repetitions problem is a great example of this. How many different ways can you distribute 5 balls into 3 bins? Well, when you go to model this counting problem with this general model here, right? Well, look, here's the elements you're choosing from, right? And here's the bins. That's got to be the way you're going to model it. Well, no. These are going to, this is really confusing. The way you model this is a combinations with repetitions problem, and I'll go ahead and actually put it up here, is the slots, which we sometimes call the bins, are going to be the balls. Here's the 5 balls, right? And we're pulling from, if this is 1, 2, 3, we're choosing 3 bins. This is where the repetition comes in, because you can choose a bin and it repeats. If you put ball number 1 into bin 1, well, you can put all of the balls into bin 1 if you want, right? but the order doesn't matter here. You have repetition, so it's combinations with repetition. But you see how that terminology is really confusing? You could have, if you're in a certain circumstance, you're picking from a group of people, right? You have a big group of people, and you're picking from that group. But it might be the case that you're going to make the whenever you go to model the problem, the group you're picking from is not going to be the people. It's going to be something else. And the slots, you're going to be like applying that to each person. This would be Jack, Kate, Logan. And you're picking from something that doesn't even seem like an object or an element. It doesn't, right? Whenever you look at a problem and you see and you're counting objects, your first instinct is, oh, well, I'm going to be picking from those objects. Maybe not. Maybe the objects are going to be the slots here. And you're going to be picking from something that doesn't seem like an object at all. So you really have to push yourself to be extremely flexible as far as whenever you're modeling the counting problem, what you're labeling as the bin. Because like with combinations and permutations you're pulling from the same group. What's the group? And when you pull from the group, you're putting them into slots or bins. What's the bins? You have to be very flexible. Okay? And it's the same idea with pigeonhole problems. Whenever you're presented with any kind of pigeonhole problem, the way you're going to solve it, the whole way you solve it, okay, is you're going to have to take a step back and break things down. You might have to do some counts to figure some things out. But the whole goal is you're needing to identify for this problem, what is the pigeonholes and what is the pigeons? That's the whole goal. That's the hard part. For more complicated pigeonhole problems, what is the pigeonholes and what is the pigeons? And then you're going to need to get an accurate count of how many pigeonholes there are and how many pigeons there are. So you might have to do like a little side counting problem to get how many pigeonholes there are and how many pigeons there are. And then once you have that, well, then it's easy. Then you use once you've got accurately figured out how many pigeonholes and pigeons there are, just use the formula. So the hard part is figuring out, identifying what are the pigeons, what are the pigeonholes, and getting the number of each correct. Okay, let's take a look at some examples. Among 50 people, what is the number of people that must be born in the same month? Okay, so what are the pigeons? What are the pigeonholes? And also, like, what are we solving for, right? For the formula, like, also, like, what are the pigeons? What are the pigeonholes? What is C? And what are we solving for? Okay, so it looks like N's going to be 50. But again, be careful with that because it can be very deceiving. Oh, 50 people, that's the N. But it looks like that's going to be the case here. What is the number of people that must be born in the same month? Looks like we're solving for C. Okay, and so what we've got here is it looks like the pigeonholes are the months. There's 12 months in a year, right? And the pigeons are the people. So it could be the case that all 50 pigeons go into January, possibly, right? But with these pigeonhole problems, it's always the worst case scenario is what you're trying to figure out as far as, okay, if they're all spread out as much as they can possibly be spread out, then it must be the case that there's no way one of these pigeonholes can have less than this number. There's no way. What is the number of people that must be born in the same month? There's no way around it. So, okay, it's N is 50. K is 12. And we're solving for C. That's it. Okay. $4.17, so you round that up to 5. So the answer is 5. How many students in a class must there be to ensure that 3 students in the class get the same grade? Okay, so what What are the pigeonholes? What are the pigeons? And what are we trying to solve for? What are the numbers? Okay, so how many students in a class? Sounds like we're solving for n. Okay, 3 students in the class get the same grade. Looks like we have C. It looks like the pigeonholes are the grades. So let's verify this. A, B, C, D, F. And you've got the students, right? So you could take all the students and they could all get A's. So kind of talk through this. Make sure the logic is right, that you've got the pigeonholes and the pigeons identified correctly. Or they could, they could be distributed, right? So this makes sense. And the question is, what's the total number of students necessary to ensure that no matter what, there's going to be 3 students that get the same grade, right? So n can't be 3 because that could be the case where you have all 3 students get A's, but one could get an A, one could get a B, one could get a C, right? So what we've got here is we don't know n, K is 5, and C is 3. So it's just that n divided by 5 is going to be less than or equal to 3, greater than 2. So multiply everything by 5. So 10 divided by 5 is 2, so 11. That's the minimum. Yes, if we did 12 divided by 5, if n was 12, then the ceiling function would also equal 3. But we're asking for it's saying the minimum. So it's 11. Okay, a theater holds 1,300 people. How many seats need to be filled to ensure that at least 2 people have the same first and last initials? Okay, so is n equal to 1,300 here? Maybe. Okay, the theater holds 1,300 people. How many seats need to be filled to ensure that at least 2 people have the same first and last initials? So no, that we're actually solving for n here. We're solving for n. The pigeonholes are the different possibilities for first and last initials. So this would be, like A and B. A person whose first name starts with an A, last name starts with a B. This would be A and C. This could be A and A. Those are the pigeonholes. So what are the total number of possibilities for a first and a last name? Or starting with a certain letter. Okay, well, that is a permutations with repetition problem. With 2 slots. Here's the letter for that the first name starts with. Here's the letter that the second name starts with. And we're picking from the alphabet, 26 letters with repetition. We could pick an A first, we could pick an A second, it doesn't matter, right? Well, we know this is easy. It's just you do the number of slots, here it's 2, or no, it's the number of objects, 26, to the power of the number of slots. So 26 squared would be 26 times 26. It would be like if we were doing a string of 2 bits, or 3 bits, let's say, picking from a 1 and a 0. Well, this could be, you could have 1 0 0 0 1 0 0 0 0 1 1 0 1 1 1 1 1 0 1 0 1 0 1 1, and that's it. There's 8. It's 2 to the 8, 2 to the 3rd power, 8. Okay, so 26 squared, that is the number, that's the pigeonholes, right? There's 26 squared pigeonholes. So what is that? 676 pigeonholes. Okay, and the C is 2. And we're trying to figure out what n is. We want to see what's the minimum number of seats that need to be filled to where at least 2 people are going to have the same first and last initials. Okay, so this is, we've got n divided by 676 can be greater than 1. So 676. $13.52. Okay, the minimum is $6.77. Okay, there are 38 different time periods during which classes at a university can be scheduled. If there are 677 different classes, how many different rooms will be needed? Okay, what are the pigeons? What are the pigeonholes? What's the C value, and what are we solving for? All right, so it seems like it could be the time periods might be the pigeonholes, right? So let's think about that. We've got these different time periods, and then these classes would be the N. So we could put a class in like the 8 to 9, another class in 9 to 10 on Thursday, right? They give a day as well. So like 8 to 9 on Monday, 1 to 2 on Thursday. Okay, and so that might not be right. It could be that the classes are the pigeonholes. Well, no. Okay, no. We've got, so there's 38 time periods during the week. Those are the pigeonholes. So we're just trying to figure out if you want to distribute the 677 classes as evenly as you can. But if you've got multiple classes in the same time period, then that means you're going to need two separate classes, two separate classrooms. Because this is Thursday from 8 to 9. This is Friday from 1 to 2, right? And these are the classes like biology, chemistry, etc. 677. So if you start having to put multiple classes into the same pigeonhole, you're going to need multiple classrooms. So what's the minimum amount of rooms you're going to need? Well, okay, this is going to be, you do 677 divided by 38, the ceiling function. We're solving for C here. $18. Okay, so that's the basics of the pigeonhole principle.